Okay, let's start. We have already heard Anirban scholarly yesterday. So Anirban is from Seoul National University, and he did his PhD from TIFR. Then he was in SAC, and his second postdoc. So we'll be talking to us about mesoscopic quantum systems to detect light.
Thank you. Thank you very much, Sarah, for the introduction and for having me here. And thanks everyone for coming. So this is a topic that I started working on relatively recently, only earlier last year. So I've been learning a lot and very excited about. So To begin with, I want to draw your attention to uh, the parameter space, the mass range of the dark matter that's possible today, even after all the observations and constraints. So it ranges from 10 to minus 22 electron volt to all the way to roughly a few tens of solar mass. And so you can see that there's a huge, many, like about 90 orders of magnitude. And so far, we don't have any clue where dark matter is. And there are some particular parts of this parameter space where we have put a lot of effort to look for dark matter. So one example is this WIMP dark matter, which is roughly 10 GeV and TeV range. There is the axion, which is the wavelength dark matter, very light. But so far, no conclusive signal yet. And this also tells us that we have to adapt our search strategy for dark matter depending on what mass range of dark matter we are.
What is
Yeah, this region. Yeah, it's like where dark matter is wavelength, because we know that the dark matter is non-relativistic today. You can compute the Debye wavelength of dark matter just 1 over m times velocity. So, and if you compute that, it's more like so the Debye wavelength is much longer than your typical other particles. So that's why you call them wavelength dark matter. So also the experiments that we do in that part, in that region, that's also a big difference from the particle like dark matter. So yeah, so
the axion is also the particle length, which also sits in that room.
yeah, so it's a wave like dark matter. We usually call it a wave like dark matter rather than. Yeah.
It's like a particle.
Yeah, it is.
Like fire.
Yeah. So you could also, of course, axion could be dark matter. That's a dark matter candidate. But you could also produce axions in other ways. So, for example, you could produce. Yeah. So the QCD axion, yeah. So if you're talking about QCD axion, which is dark matter, then its wavelength is much longer, depending on the mass exactly, and it would be wavelength. It can decay into other particles, of course, but I mean, practically for practical purpose, we just call it wavelength dark matter. But I mean, it's only a bookkeeping thing whether you call it a particle or wave. It's all like the theory, underlying theory is just quantum field theory.
What is the skill that characterizes the wavelength?
You mean, sorry, what is the characteristic wavelength for?
Yeah, beyond which you call it as a wavelength, below which you call it a particle length.
So
Yes.
yeah,
particle like
it's not a very well defined boundary, but I can say that typically if dark matter, if you're talking about dark matter mass below, let's say EV or milli-electron volt, it would be like a wavelength. Typically it's called wavelength dark matter, but sometimes people also call them particle dark matter. But yeah, it's only a bookkeeping thing. There's no technical form of that. Yeah, but yeah, you could say that. Yeah, that could be one way to say when it's wavelength. But for dark matter, I mean, the quantum wavelength is just 1 over m, and the Debye wavelength is 1 over m p. So you already have a relation between this two. It doesn't matter what the mass is. But yeah, but what I want to just say that it's more like a just like demonstration purpose, or just to talk about dark matter. But technically it has no bearing on. I mean, it depends on the way you do experiments, but that's about it. So I can start with the classic weight regime. So if the probably the main motivation behind this type of dark matter was the supersymmetric theory. It's typically within the mass range of 10 GeV and 10 GeV. And there are multiple experiments that are going on all over the world: the xenon, lux zeppelin, Van-Dyck's, cosine, all of them more or less they have the same technique that they use some novel liquid, typically in this case xenon, two-phase, so liquid xenon and gaseous xenon. And the idea is that dark matter will come and hit one of the nuclei in the xenon detector, and that will create and prompt flash of light. That will create one signal, and then this will also release some electrons which will drift over applied electric field, and on the interface of liquid and gas, it will create another flash of light, and that gives you another signal. So then you can reconstruct where the scattering actually happened, and if you see some signal, then you can go back and calculate whether this signal is okay with your expected dark matter scattering there. So xenon is used because because we are trying to look for dark matter in this heavier mass range. It's good to have a heavy nuclei so that the energy exchange between the dark matter particle and the detector, the nucleus in the detector, is efficient. So, and that happens when we have comparable masses. So xenon it's also a noble liquid, easy to handle. So so that's why we use xenons. And this is the latest constraint that we get from this one is actually from the LZ experiment. This is the dark matter mass, and the y-axis is dark matter nucleon scattering cross section. And the solid black curve is where we are at right now. So roughly it's a little bit below 10 to the minus 47 centimeters square. But that's only like a heavy wind regime. But to the left, for lighter dark matter, there are many more dark matter models that we want to explore or rule out. So these two plots are taken from a SNOMAS report last year for dark matter electroscattering cross section. Both of them, and this one is for heavy mediator, and this one is for light mediator. So you might see these terms heavy mediator and light mediator in some of these plots today, and that just means that when dark matter interacts with the normal matter standard model, usually have to assume some models, an underlying particle model. So the mediator that couples them, that could be heavier or lighter compared to the typical momentum exchange. So this just means whether the mediator is heavy or light. So you can see that all these lines are basically the cross section that you predict if you want to produce dark matter in that particular model with the correct relative values. So and this gray region here at the top is the region which is currently excluded by experiments. So we have many orders of magnitude to look for, and similarly for the light mediator case. This is the already excluded part, and freezing is the main part of the parameter space that we want to explore in the near future. So that's kind of the motivation to go for light dark matter. And this is again another set of plots, but in the same parameter space. These orange bands are those theoretical models, the part of the parameter space that I showed in the previous plot. And this green part, so first of all, you see that below GeV, roughly GeV or tens of GeV, there's a whole lot of free parameter space that we still have not excluded yet. But there are some plans, of course. These green regions are the parts where we expect to see some constraint within 5 or 6 years, next 5 or 6 years, and our term is even beyond that. So this is the current scenario. We don't have any anything concrete yet, any concrete results yet, but we hope to do some useful experiments in within the next decade or so. Now the thing is, going to the lighter mass dark matter is that the typical energy deposited by dark matter scattering also goes down. So we know that dark matter is non-relativistic, so its energy is just half in this way. And similarly, the momentum is just NP. So you see that it just linearly scales with dark matter mass. So if you go to the lighter mass, the energy also goes down. And today, among all the experiments, all the direct detection experiments that we have done so far, the lowest energy threshold that we have achieved is only of order of a few electron volt. So yeah. So now the outline of today's talk would be, first I'll give a very brief overview of the different techniques for light dark matter detection. And then I'll talk about a new way of doing direct detection experiment for light dark matter that we have proposed. And then another idea that I'm right now working on electron scattering in graphene, so using graphene as dark matter detector. And finally, it's not my work, but I just want to mention about this topic, the synergy between quantum computer research and light dark matter detection, which I find very interesting. Now, I said that when you go to lighter mass, the recoil energy or the deposited energy also goes down. So if you come down from the top, so at a very high energy, yeah, in the keV range, we have been using the liquid noble gases. So this is this pink band, and below that we have some ideas of some experiments that use semiconductors. And so typically semiconductors have electron bands. So now if dark matter scatters with electron, that can excite the electron from the conduction band to of any lower band to an upper band. So and you can look for that electric charge. Below that, we can use phonos. Phonos are just crystal vibrations, the quanta of crystal vibrations, and there are ways to detect phonos, and I will actually discuss in detail about phonos because that's also related to my work. And finally, at the very bottom, we have the superconductors and superfluid helium, and also some single photon detectors, phonon detectors. They have typically the energy gaps of tens of milli-electron volts or a few tens of milli-electron volts, and that's the lowest that we have so far till date. Depending on which mass of dark matter you are interested in, you have to use different techniques. But it's not all challenging. So there are also good things about going to lighter dark matter, which is the number density. So your experiment depends, the sensitivity of your experiment depends on the local dark matter number density, which is n5. But you don't know the number density. We only know the energy density, which is local. So, and we divide that by the dark matter mass. And so now you can see that if you go to lighter dark matter, you can actually have very large number density. So typically, the sensitivity increases for lighter dark matter. So you don't need a multi-ton scale experiment or detector to get a world leading or competitive limit for such EV dark matter. You can have a gram scale or tens of grams scale, hundreds of gram scale detector and do some very nice experiments. This is the local number density, yeah, within our solar neighborhood.
But then when you get this dark matter density from the planet data.
Yeah, that's the cosmological density. Yeah, that's much less. That's I think about 5 orders of magnitude less than something. This is because we are sitting inside a halo, so the number density is much higher. So I said that just below the liquid noble gas energy scale, we can use some semiconductors, or actually these experiments use CCDs or charge detectors, and this is everywhere in where if you have a camera, you have a CCD. So the idea is that there is a semiconductor, and it has electrons. So the electrons are at the ground state. Electrons are sitting inside the valence band, And if dark matter comes and scatters with one of them, they can be excited to the conduction band. And if you apply an electric field, these electron holes there that can travel to your electrodes, and you can detect that charge. And nowadays, with these experiments, we have such sensitivity that we can actually detect single charges. So the example, the type of experiments we have using this technology are Sensei and DAMICAM, and there is a future collaboration which might form, might happen with Oscula. So from these experiments, we have this limit. So to the left, this is a plot from the Sensei paper, so this blue region is the current exclusion limit, and to the right here is from the DAMICAM experiment. So the solid black line, they are most of both of them are more or less comparable right now. And these lines are for future projections. So Sensei, DAMICAM, and Oscula. Hopefully, these will cover some of these interesting dark matter models within maybe next decade. Now, going even further below, we can excite actually phonons inside the detector from dark matter scattering. So I said that phonons are basically the quanta of crystal vibration, and this happens because if there is a kinematic matching between the energy scale and momentum scale of dark matter and the energy and momentum scale of phonon, then the possibility becomes large that the dark matter will actually excite phonons instead of scattering a single recoiling an individual nucleus. So the typical momentum scale of phonon is roughly the inverse lattice spacing. So in any crystal, you have some regularity with the periodicity, and you can define a momentum from that. And that's typically of the order of few kg. And the corresponding energy range is 100 millielectron volt. And so if you go below MEV, mega electron volt, then you can actually use phonons as the primary excitations in your detector from dark matter scattering. And for this to happen, you actually need dark matter to couple to the nucleus, because then you can excite phonons very efficiently. If you couple only to the electrons, it becomes very difficult because electrons are not very tightly coupled to the lattice. So, yeah, the quantum, the particles.
I'm asking you guys, how many? So when you say that the upward from the balance part to the conduction, that picture was very clear from the moment that
yeah.
But when you were saying that in this case, so the phonon is like if you have like the kind of harmonic motion in the crystal, then only you can get the result. So how can I picture this game?
So
the scattering of the phonons.
Right, exactly. So if you start with a very heavy mass dark matter, then the corresponding momentum is the incoming momentum is also very large. So and that momentum is actually the corresponding length scale is also much smaller than the lattice space, the inverse lattice space. So in that case, what happens is that all of that momentum is imparted to a single nucleus. So and then you see the nuclear recoil. So that was the first idea. But now, if you have a much lower energy dark matter, the dark matter is actually not seeing a single nucleus. It's actually imparting its energy over multiple lattice sites. So that's why it's creating these crystal oscillations in the detector. Yeah, right. It's just like the theory of neutron scattering that we have that we know.
The dark matter particles don't detect standard model particles or in this mastering.
It of course it has to have some interaction with the standard model particles.
So how does it couple? Indirect coupling?
What do you mean by indirect? It just couples to the, you can couple to the proton or neutron or whatever.
But it doesn't then violate any other constraints which are there.
No, it's just like the normal coupling that I showed here. yeah, for example, in this case, dark matter neutron cross section is the same cross section that you can have. But now you're not here, you are just, you are somewhere here, the lower mass, sub MeV mass range. So the scattering energy is much less. So then actually phonons become the primary mode of excitation. It does same, you can have the same type of model. There's nothing.
When you say that there's the interaction of the phonon, that it's cross section with the electrons or nucleus or the charged particles is much more than other electric particles. That's why you're looking at this mode of interaction.
No, yeah, the thing to understand here is that phonons are not some new type of particle, fundamental particle, right? They are just, sorry, it's
phonons are not, you can write it as a low energy effective theory coupled to the electron coupled to the lattice chain, which is nucleus.
so
Like a regular pattern. Phonons are nothing but vibrational mode.
phonons are just the vibrational mode of the lattice space, and these phonons, they exist only on the lattice, right? They don't have any independent identity or independent signature. So
Somewhere low energy effective. But it is like
okay, it is a low energy effective theory, but I'm not sure if you can call this a low energy effective theory of QED. But what I'm trying to say is that these phonons, they live on the lattice only. So if dark matter couples with nucleus, that's the only requirement. If dark matter couples with the nucleus, you can excite phonon if the energy is low enough.
but then so you are mainly looking at so when you tell dark matter is coupling with the nucleus, you're looking at the strong scattering cross section on the nucleus.
No, it's a beyond standard model. It doesn't cannot be weak scattering or weak interaction or strong interaction.
Why do you call it beyond standard model? Because dark matter is beyond standard model. It interacts with the standard model particle.
Yeah, but yeah, beyond standard model in the sense that that interaction was not included in the standard model of particles. So that's why, in that sense, it's just beyond standard model. But the only new physics here is that you need some interaction between dark matter and nucleus, proton, neutron, or whatever. And yeah, so then if you tune the energy, you can go to very large energy. In that case, a single nucleus will be required, and the experimental signatures will be very different. And if you tune the energy to very low, you will actually excite multiple lattice sites at the same point, and that's basically the phonon oscillation or crystal oscillation.
And these kinds of cross sections don't violate any other principles, like for example, they not affect any other physics.
No,
Like
yeah,
nucleosynthesis or not affect any
no. So for nucleosynthesis, there are some constraints. So this part of the exclusion region is coming from ineffective. Similarly here, where if for example, if dark matter is lighter than MEV, it can be thermalized in the early universe during BBN, and that would have some implications for the light element abundance observations. So there are some constraints. So these are those constraints, but they are already shown in the parameter space. So, but still, even given all of them, we still have a lot of space with. Sorry.
And there are no other bounds for any other cases which can constrain these parameters, because then of course you can, there are large parameter space, then of course it becomes more difficult to constrain or
It is difficult to constrain. I mean, it might still, you might say that it's only a few orders of magnitude, was the big deal, but it takes quite an experimental effort to go from one order of magnitude to another order of magnitude. So yeah, it's a lot of parameter space. But my point is that we have done a lot of experiments in this part, in the heavier space, heavier mass range, but that has not yielded anything. I'm not saying that we should stop looking for dark matter in that part, but there's also a lot of parameter space that we have not looked at. at the lighter mass range, and we should broaden now the search to a wider mass range. So that's the only point.
So at this stage, you're being agnostic about the BS kind of BSM interaction that
Yeah.
the dark matter particle has with the nucleus, and
Right.
it's just an effective kind of interaction that you're considering.
Yeah.
And you're also not considering the type of the dark matter, like whether it's particle or scalar at this stage, and
Yeah.
so
Right.
everything would hold whatever the kind of
Yeah.
model we might have in the future.
Yeah, exactly. So in this case, you can see that this is the name of the model. So here, for example, here dark matter is Margana, here it's scalar, but all of them have some predictions in this character space. Yeah. But yeah, from the experimental point of view, this cross section is just an K parameter.
Are these phonon experiments done at room temperature or?
No, you need a cryogenic environment because we also want to be the background. I'll tell a little bit about the. Yeah, you want to be above the thermal background of phonons. So phonons are everywhere. Any material has some phonons that's proportional to the temperature of the material. So you want to cool down your detector as much as possible.
You want to only look at the nucleus recoil.
Yeah.
When the dark matter enters of the nucleus, you want to look at the recoil.
Right. Yeah.
And since there are many dark matter particle density is large, then of course now if you solid detector, then there is a lot of recoil happening.
Right. Yeah.
The collective effect of them.
Yeah, there are ideas to detect multiple. I'll actually talk about that in a little bit. I think I completed this slide, and so a little refresher about the phonons again. So as I said, phonons are basically crystal vibrations. Any crystal has at least 3 phonon modes. These are called acoustic mode. This because we live in the 3 dimensions. So yeah, you have this 3 reactions of vibration. But there are also possibility of optical mode. So the example of that is aluminum, which is a very popular detector for dark matter. So this is the energy momentum relation of phonons. So you can see these 3 lines are the 3 acoustic modes. But if the unit cell of your crystal has more than 1 atom, it can also have optical mode. So it's basically when the atoms are vibrating in the opposite direction. So so they can actually cancel their momenta in individual momenta, but still they have some finite energy. So for example, in silicon, it has 2 atoms per unit cell, and these are the optical modes. So you can see that 0 momentum, they have finite energy. So depending on your requirement, what type of excitation that you want to see, you can use different types of materials. And there are experiments that try to that use phonon excitation by dark matter. So the examples are CRESP and SuperCDMS. This is used to be in the US, now it's in Snowland, and CRESP is in Europe, Francis lab. So CRESP uses calcium tungsten as a detector here, and in case of SuperCDMS, it uses the silicon and also germanium. So the idea is that in this absorber block, which is called substrate, dark matter will come and excite some multiple phonons, and these phonons, this block is actually covered with some superconducting aluminum pin. So this phonon, some of these phonons will travel to this pin and they will break Cooper pairs, and then you can detect the individual broken Cooper, the charges released from these broken Cooper pairs with this transition edge sensor. And similarly for the CREST uses a little bit different technique. It also uses the scintillation light in addition to the phonons. And again, here you can they can actually detect this scintillation light using this TES devices. By the way, TES stands for transition edge sensor, which is a superconducting based device, and These are basically very sensitive calorimeters, so they can detect very small amount of heat increase in your device, and that's what
Bolometer.
I think they're called calorimeter because they are trying to sudden increase in temperature in the device. Right. Okay. Yeah.
You consider random model for the interaction standard model of that. Standard model can have different.
Yes.
Considering the random.
Oh, sorry, what is random?
You said that there are different, it can be scalar or matter.
Yeah. Right. Yeah.
So the probability that probability will be smaller than
I guess it has to be stronger than the gravitation. Yeah. Okay. Yeah.
but then what about those CMB you get
Right.
theoretically
Right.
on like
Yeah. Yeah. But the constant that you get from CMB, those are also there, but they are not very strong at this moment. So there are other experiments which keep much stronger boundaries. Yeah, but there is constant from CMB also.
that's completely different. This one will have, this one will say that it will be stronger effect than gravity. It should be visible that CMB difference.
No. We are trying to go to smaller cross section, right? You go to smaller cross section that is scored by CMB. We don't expect any further signature in CMB, right? It's you are talking now talking.
Feel larger, the cross section.
Sorry, I don't think I get your point. So when you say that so now we can say that what is the signature in CMB when there is only gravitational interaction between dark matter and standard model. So that's a different story. So that's that has nothing to do with this plot. In that case, you don't have this plot at all. There is no interaction between dark matter and standard model. But now we are hypothesizing a new interaction between dark matter and standard model, which is non-gravitational. And stronger than gravity, yeah. So then now we can talk about signatures in different places. So there's signature in CMB and also in laboratory experiments. But CMB, in this case, the CMB does not do as good as some of the laboratory experiments. So the constraints that you get from CMB are much weaker than the laboratory experiments. Yeah. So then next topic is this new idea that I did, the work that I did with Noah and Rebecca, to use the power measurement by quantum devices. So the idea is that all of these data detection experiments that I talked about so far, they are looking for recoil rate, right? So you take the event rate spectrum of dark matter in your detector, and then you calculate how many events are possible. So it's like looking at the individual recoil of dark matter. But our idea is that today we have such sensitive devices, small quantum devices that can measure power very accurately. You can actually look for multiple scattering of dark matter within your detector and place some competitive bounds from that. So in this case, mathematically it just says that you just multiply the event rate spectrum with another factor of energy, and then you get your power. This would be helpful, of course, for halo dark matter, but it's also there is also another population of dark matter which is called captured dark matter or thermalized dark matter. The idea here is that, so this is not my work, but it's very interesting. So we also look for them. So the idea here is that if you have relatively large cross section between dark matter and standard model, it can get, so dark matter is coming from the outside halo, and it can get captured through multiple scattering within any astrophysical object like Earth, the Sun, and over time there could be a buildup of dark matter population near the surface or throughout this astrophysical object. So in these papers, people have shown that it's possible for certain cross sections to have a very large population of dark matter near the surface of the object. It happens only within a certain range of parameter space. So, but the point is that because this is a thermalized dark matter, the temperature or the typical energy of these dark matter particles are much smaller than the halo dark matter. So if you compare the energies for the same mass, you can see that this is a much lower energy, lower velocity. So you need low threshold devices to look for this thermalized dark matter. But there the advantage is that the number density of these dark matter will be much higher. So it's a 10 to the 10 is just a conservative number. It could go up as large as 10 to the 14 or 15 compared to the order 1 fraction number density for same mass halo dark matter. So we'll also look for that this population of dark matter in addition to the halo dark matter. This is basically the underlying mathematics here. I'm not going to go into the details of this. Just want to point out one thing. So this is the total scattering rate. Of course, this is proportional to the number density, the cross section, the dark matter nuclear scattering cross section. We integrate over the dark matter velocity distribution, and finally we have this function called dynamic structure function. And this basically says encodes all the information of your detector for a given momentum and energy. So this is the quantity that comes from the condensed matter side or your detector side. Yeah, and you want to calculate that. So as I said, at low energy, phonon excitation is a primary mode here. So we given our knowledge about the neutron scattering, which is very helpful. We don't have to reinvent the wheel here. We can actually calculate this structure function that I showed in the previous plot in different regimes when the momentum is smaller than the inverse lattice spacing or when it's larger than that. And depending on the regime, also you can excite single photon or multiple phonons, say a single phonon or multiple phonons, and you can calculate the respective forms of the structure function. So this is all analytical approximation. This was shown in this paper. You could also do some experiments and use the experimental data instead of using this analytic approximation, but this is much faster and you get very good result just by using these functions. So these plots are this structure function, this heat map in the momentum and energy diameter space. So the brighter the color is, the easier it is to excite phonons. This vertical line here is that Briouson momentum of the inverse lattice spacing. The left one is for aluminum. This one is for silicon. Aluminum does not have any optical mode, so there is no line here, only the acoustic mode. And here it's dominated by multiple phonon excitation. Similarly here, but in addition to that, it has an optical mode here. So once you have this structure function, you can calculate the dark matter scattering rate, or in our case, you can actually calculate the power injected by dark matter in your devices. So then you can, but then we use some experimental data actually. We use the data from three different experiments. So the first one is this. They were trying to build, so this is not a dark matter experiment at all. They were trying to build a superconductor free of quasi-particles, so free of any background quasi-particles. So this is a superconducting island, which is junctioned with a normal metal. So, and they were trying this tunneling of quasi-particles released from breaking of a Cooper pair. And they show this result. And then you see this, there's a background density of quasi-particles in the device. And we use this number to back calculate how much powering is being injected without any source that's creating this background. And that gives us this number of roughly 10 to the minus 25 watt per micrometer. So this is one experiment.
That acts as your noise background.
Right, yeah. We are just being very conservative. We are not saying what's causing this background. We're just saying that dark matter power should not be more than this. Yeah.
So, what is actually
because of the dark matter scattering, yeah. And the second experiment is again, this is not a dark matter experiment. They were trying to build a very sensitive single photon detector for space telescopes. So they have the superconducting conducting detector here, and they are shining photons from a source. So you can see in this plot, even though they were not expecting any photons here, they had some photon count, which is dark count. And we take this number very conservatively and say that the dark matter number cannot be more than this. And then this actually gives a bit larger power, 10 to the minus 20. And the third one is actually a dark matter experiment, the super CDMS experiment. In the experimental collaboration, they were trying different things, but what we said is that before they can do the experiment, they have to calibrate their device and they have to fix the 0 point of their energy and 0 point of their power, so that they can say that anything above this number would be counted as an event. So we took that 0 reference point and converted that to power density, and that gives us 10 to the minus 21 watt per micrometer cube. So this is the result. This is again dark matter pattern cross section. The gray regions are other experiments and observations. This orange line here, this contour here, is the limit from the first experiment. This magenta one here is from the super CDMS experiment, the third one. And the second one is actually sitting up here, so you can see it here. So you see that although it's not going into the new part of the parameter space, but still it's very competitive with some of the other experiments. And this is only the beginning. So in future, these devices are going to improve much more. And hopefully we'll have much better constraints then. So these are for the halo dark matter. You can also do the same for the thermalized dark matter or the capture dark matter that I told you. And so this blue contour is for that. In this case, we are not actually limited by the sensitivity of the experiments at all. We are limited by the evaporation. So if you have a very light dark matter can get kicked out by the thermal agitation of the medium. So the capturing process is not efficient. So there is not much capturing to the left of this parameter, to the left of this blue contour. So we are only limited by that. So this was the result in this paper. And right now we are working on trying other different types of materials which has better phase matching with dark matter energy distribution, and hopefully we'll have some better results with that. So this is only limits, right? We're not claiming we're trying to discover dark matter. To actually say that there's some power injection by dark matter, we have to be very, very careful to isolate the dark matter part from the other part. So you have to know your device very well for the calibration. Also have to look at the other types of backgrounds, neutron scattering, radioactivity, and cosmic rays, which are the typical known background in any dark matter experiments. And there could, of course, there could be some unknown systematics. That's always a possibility.
Sorry, the previous plot, I can just ask one thing. So
Here or
yeah,
okay.
so the limits, if you compare to this kind of cross sections, is much deeper, right?
Yeah.
And I guess that's because of the low mass of this. So the recoil energy is very less. Is that the way to understand that?
Right. Yeah. So the wind in the wind regime, the typical experiments they use the nuclear recoil, and this small dark matter does not have enough energy for nuclear recoil.
So, however, to get the right density, the number density should be much larger with low mass, right? So that doesn't help you in some way. It's a single
the number density.
Yeah. So it's a single scatter, right?
It does help. Yeah.
It does help.
It does help. So the number density
not enough to bring it to that same kind of.
Not yet. Not yet.
Yeah. That easy to see why.
So it has to do with the size of the detector. So even though number density going up, but still it's always better to have a bigger detector so that you can increase the number of possible scatterings.
Sure.
And with these quantum devices, the thing is that they're so
nowhere close to the wind.
No. Yeah, these are very small devices, and we are already limited by other.
Explain the entire like loss of sensitivity. I mean, if you make the same size of detector, then you can.
There will be so much background that you won't see anything there.
No, but independent of all that. But at least in terms of getting back the sensitivity, you should be able to get.
In principle should be, yeah.
And here we are looking at a single scatter, that way.
In this case, in our work, we are looking at multiple scattering. So it's a collective scattering and that gives you a total power. So quickly, I'll mention another work that I have been working on. This is in collaboration with a condensed matter theorist in my department. So so the idea is to use bilayer graphene as dark matter detector. So you probably already know what graphene is. So graphene is a hexagonal lattice of carbon atoms, and if you put one layer on top of another, you get a bilayer graphene. But the interesting thing about bilayer graphene is that if you draw the energy momentum diagram of electrons in this layers of graphene and apply some voltage across the surface of the graphenes, you can actually open up this gap between the valence and the conduction band, and you can tune the size of the gap with the voltage of your gate, and which is very nice because that gives you a very good handle on building your detector. You can actually change the threshold. So yeah, so the idea is to use this as a dark matter detector. And the way to go with this is to use this was shown in this nice paper to that the linear response of any medium is related to the dielectric function of that using the fluctuation distribution theorem. So epsilon is the dielectric function, and I is the linear response of a given momentum of energy, and this is the Coulomb potential that's just coming because electrons in any medium, they are interacting with each other through electrostatic potential. So you can use that, and then this coming back to the same quantity, the dynamic structure function, that is actually related to the linear response, which is again related to the inverse of the imaginary part of the dielectric function, typically called the energy loss function. And this function then again goes to your dark matter scattering rate, and you can calculate how many scatterings you can expect. So the only thing to do is to compute this dielectric function. So for some materials, it's experimentally available. So there are some already condensed matter experiments which gives you the epsilon in certain parts of the momentum and energy parameter space, or you can also calculate this from the first principle. So in this case, we are actually trying to calculate the dielectric function. So far we have this plot here. This is again dark matter. In this case, of course, dark matter electron scattering, and these two lines are for two different band gaps, so 50 and 100 milli-electron volt. You can see that the projection is almost touching the freezing curve here, and this is for a exposure of 10 milligram here. And if you compare this with some other experiments, other ideas, which is, for example, the superconducting aluminum, so it can actually beat the superconducting aluminum by gram per gram basis. So we are still working on this, and hopefully we'll have this paper out next month or so. Towards sorry, I can get you last word. Yeah. Yeah. You're right. Yeah. So it's been difficult to say why, but it might have something to do with the better electrical conductivity of graphene. So graphene is a very nice electrical conductor. So yeah, I mean, to exactly the pinpoint the reason. So we are still working on that. So we have not figured out everything, but yeah, it turns out to be better than that. Yeah, in the superconductor, the idea was to break the superconductor.
The normal part of the superconductor, like the transition from superconductor.
Yeah, something like that.
So electrons are now captured by the field.
Yeah, exactly. So typically what happens is that you can put your superconductor, so you know this plot of resistivity versus temperature. Then you set up your device so that you are sitting at the middle of this sharp transition. So even if with a very small amount of energy deposition, you can get very large change in the resistivity. So yeah, it's kind of in the middle of superconductor and normal metal state.
Where do you change, look at the change in the resistivity?
Yeah, or you can detect the number of.
That number of times. Fraction of the purpose.
Yeah, so this idea does not have the power measurement. This is just a single scattering of dark matter.
Oh,
Yeah, this has nothing to do with the power measurement. Yeah, this is a separate work.
this is not superconducting, right?
The graphene,
Graphene kind.
no, that's not superconducting.
So you're interested in this.
Yeah, right.
So is it all projected limits, something easy?
This is superconducting aluminum. Yeah, this is a projection. This is not an actual limit. The actual limits are here. I think there is also some ineffective bounds which I did not put in, but it's somewhere here.
So this has the promise of being much more sensitive than the previous point.
Yeah.
And is there any assumptions on the kind of interactions, or this is very generic? Or
Very generic dark matter electron interaction.
this will be the best kind of experiment?
Yeah. Yeah. Right, for the same amount of exposure. But there are of course other challenges. I'm not sure if I have I don't have a slide on this. But of course there are challenges like getting a lot of graphene in a single piece is very difficult. But getting a superconductor, reasonable size of superconductor is easier. So there are also these things. But ideally, gram by gram comparison, graphene would perform better than aluminum.
So this includes background, what about thermal noise that is not taken into account?
So when you show this projection, so these are like the proof of principle papers. So when you show these projections, we don't consider the background. We just say that we have to see 3 events within some exposure time. So in this case, 10 milligram year exposure. So you can say that 10 milligram detector mass run for 1 year time. So, but if you then for a realistic to do some realistic experiments, you also have to take into account the backgrounds, but that will require further study.
Do you think those can be handled? It's not going to be.
There are challenges too in the background case. If you are interested, I can also I wanted to talk about those things, but there are some things.
We can talk later.
Yeah, sure, we can discuss offline for that.
But thermal noise is not a problem.
It could be a problem. It could be a problem sometimes.
But you could always cool this, I guess. Will it
But
lose its
still-
sensitivity?
But yeah, of course, no, it will not lose its sensitivity, but still there could be other types of limitations from. I mean, I think I can talk about that later. So finally, this is the topic that I wanted to mention, which is the synergy between the light dark matter search and quantum computer research. So we know that recently there have been a great enthusiasm in the developing qubits, which are basically qubit chips. As many qubit chips on a single substrate as much possible. So far, I think the Google's Sycamore processor is probably the best one. It has 54 qubits on a single chip. Sorry,
Now
it has more. Right. Do you know what's our current number?
now, this is noisy, but it is more than.
Oh. Oh, really? Okay, but have they performed the actual calculation on with 100 qubits?
I mean, it is noisy.
Okay.
You don't have to.
Okay. And there is also a drive going on in India. So earlier this year, I think DST approved a national quantum mission. So they want to develop some nodes of research on this topic in different parts of the country. Now the idea, why is this similarity? So if you look at the left, this is the super CDMS detector cartoon, and to the right is the qubit chip from one of the Google's paper. You can see the similarity. It's basically a semiconductor substrate and some superconducting material on top of that substrate. And even though these experiments or these ideas, they have different motivations, but technically they are trying to do the same thing. In this case, they want to isolate their device from the environmental perturbations as much as possible so that they can maintain the quantum coherence across all the qubits on top of their substrate. And similarly, in the dark matter case, we want to also isolate all the environmental backgrounds to look for dark matter signatures. So there is a nice technical synergy that's going on between these two researches. And I think we have some chances, or we have some directions. I mean, there should be more collaboration between these two groups so that we can actually have we can achieve our goals much more quickly. And I personally know one collaboration that's happening in the US in the Fermilab. It's called Nexus collaboration, in which they are actually trying to use qubits as dark matter detectors. So that's still in the very preliminary stage. They're still doing simulations for dark matter signal, but hopefully in future they will have some meaningful constants in dark matter.
But how about the volume? I mean, with a single qubit, I mean, that will be, the base will be very low, right?
Right. Yeah. So that's one challenge. But even then, you can have that's what they are trying to do. If they can multiplex multiple qubits within some reasonable volume, then probably we can have some more sensitivity.
When they simulate, what is it that they can
Right, they are simulating when if there is a dark matter, if there is an energy deposition inside a qubit by dark matter, how that energy distribution changes the qubits or how it propagates inside the device, those kind of things. The details of the experiment that they are trying to simulate. That. Now, going to the future, my plan here in this direction. So as I said, I started working on this only very recently. So I'm anyway learning a lot. And one direction to go would be to use twisted bilayer graphene. So this is kind of an in between graphene and superconductor. So people have shown both from theoretical and from the theoretical side that in a bilayer graphene, if you twist one of the layers by some angles, you can actually achieve superconductivity. It happens due to some complex interaction between the electrons from these both layers, and it would be nice if we can use this property for dark matter detection also. The other idea is to use some inherently anisotropic material for dark matter detection. So in this case, you can see this is the response of the detector in the parameters in the momentum space. So QZ and QY, so in one plane. And the response is of course anisotropic. So it can help to beat some of the background. So if dark matter is primarily coming from single direction, and if you have an anisotropic response, it can actually say that which part of the which events are from dark matter and which are just from the background. So this would be another interesting idea.
Do we expect dark matter to come from single direction?
So yeah, because the solar system is moving
So
through. Yeah, right. And finally, this I just mentioned, we can try to use qubits as superconducting qubits as dark matter detector, and there's already some work going on in the quantum computer research in India, and perhaps we can try to, given the scientific community, the scientific stage in India, dark matter research stage in India, I think it's possible to do something meaningful in this direction. So
Sorry, going back to that, so that in EV, how much would that be, the anisotropy, the energy requirement?
Sorry, what do you mean by EV?
In electron volt? So that's a very slow motion, and then I translate the electron volt, that anisotropy, I would guess, is very, very tiny.
Oh, so you mean that what is the energy difference whether the dark matter is coming from this side or the other side? Oh yes, that's more. It's more like a 10% effect.
And that would
Yeah, because so the dark matter speed is like 200 kilometer per second, and so and the Earth's motion is about 30 kilometer per second. So
there would be some modulation.
there will be some modulation, right?
This is the gamma kind of thing, right?
Yeah, but there could also be daily modulation. There could be yearly modulation. There are different parts of that. And so finally, I told you about the detection scenario of light dark matter. There are a lot of the parameter space that we still need to explore. There are some ideas, there are some experiments, but still we have many orders of magnitude to cover. In our work, we propose a new way of doing direct detection experiment using the power injection by dark matter. And of course, we need further studies for detection and also background rejection. And finally, I told you about this collaborative strategy that can happen between the quantum computer research and the dark matter community. I think which will be beneficial for both. So I'll stop here, and thank you for your attention.
So there isn't any hard computationally hard problem quantum computers. There's some hard simulation problem in this quantum computers could be directly.
That well, you can use quantum of. I mean, personally, I don't think the quantum computation is matured enough to actually help us in do some large calculation yet. I mean, that's still a long way to go. It's we're not trying to use quantum computer for that purpose. We are trying to use the devices for dark matter detection.
How will you compute the value?
Yes, yeah, right. So I showed 0.4 GeV per centimeter cube. So that's right up to within like 10%. So plus minus maybe 0.03, 0.04.
How do you determine?
That comes from the motion. So there are multiple measurements. So there is one important one is the motion of the stars around the solar system. So we look at the stars which are within the local neighborhood, within the galaxy, and we try to determine from their kinematics, we try to determine how much mass is there locally, and that gives us.
Because it could be just distributed in the external. I mean, how do you determine the density? Locally, experiments have been done on we need the local.
Yeah, so this is not from some experiment. This is from the observation of the stars which are within the local solar neighborhood. So you are actually looking at some dynamics of the some region around the solar system, and that gives us the local density of dark matter. Of course, if you go to even longer length scale, galactic length scale, there is a distribution of dark matter which is a radial profile of dark matter, which is called the NFW profile, and that has some radial dependence. But within the vicinity of the sun, it's thought to be roughly 0.3 or 0.4 GeV per centimeter.
And the NFW gives you what? For this local neighborhood.
So we know that the profile is NFW, and we actually normalize the profile by fixing the density at 0.4 But that also corroborates with the total mass of the dark matter that's roughly 10 to the 12 solar mass. So,
So is it possible to not use the 0.4 and then normalize it from some other measurement and then ask how does this 0.4 compare? If there is some other area.
Yeah,
Maybe
I think you can also use the galactic rotation curve. So you can look at the stars and
That's been done, you know, like how does it?
Yeah.
Compare?
yeah, there I think
Is it
there-
consistent with that?
yeah, I think all of these observations are more or less consistent with the local star kinematics or the galactic rotation curve. I think all of them give the more or less.
This 0.4 is actually, we can tell that it is dark matter and not visible matter.
Yeah,
So we can actually partition it into visible and dark matter in the local network. We do that for galaxies, right? For the galaxy rotation.
yeah.
How is that also done for the local neighborhood? Partition the visible and dark matter. And what are the error bars in there? I mean, is it very reliable or is it tentative?
So this number, I know that this number has about 10% error bar here. But I'm not sure if we can do that, dividing the total mass from the visible part and the dark matter part locally.
Perhaps if you assume the same fraction, then you can divide.
Yeah, that you can of course.
They not have sensitivity to that. It involves, you know, like
Yeah,
estimating.
right. Yeah, I mean, there is this problem of invisible baryons or I don't know what's the technical term, but
Like
there.
groundwater.
Yeah, so the things that you can see, but they're still there.
So which collaboration is this with done this?
So one of the famous one, I think early 2000s were from the Hipparcos satellite. So the satellite with the star observing satellite, and that gave us a lot of data. But very recently, after the Gaia data came out, now we have there are also other measurements, other collaborations which have calculated the same number and more or less consistent. Yeah.
So many low energy experiments. Can you now constrain any low energy effective theory of dark matter from all of these?
You mean, what do you mean by low energy, like non-relativistic effective theory? Or so in this case, we always use the non-relativistic effective theory of dark matter. So dark matter, the halo dark matter is always non-relativistic. Its speed is 10 to the minus 3 times speed of light. That we know. So yeah, so in all of these operators, we in the calculation it is implicitly assumed that the dark matter that dark matter is non-relativistic, but
So you have a part which is dark matter coupling with another one which is dark matter coupling with electron.
right.
So can you then construct the low energy effective theory of dark matter particles that you kind of want? With all the information that is available.
I'm not sure about. So you were asking whether we can write down a like UV complete model from this.
No, I was wondering whether you could write the complete low energy effective theory with all the couplings very well constructed. And then of course you need to go to the high energy field for something.
Right. I mean, typically it's yeah. So the way actually it works is that the experimental collaboration, they are not interested in working on particular models. But what happens is that there are many groups which they have their favorite models. What they do is that you might have some complicated dark matter model which has some interactions with standard particles, and you might have some Wilson coefficients, some new physics scales. Then you can compute at low energy what are those couplings, and then you compare that with this number. Then you can do something meaningful in your coupling versus new physics scale or whatever parameter space. What are the part that is excluded and what's still valid. So yeah, there are of course studies along this line. And of course, I mean, there are so many models, it's very hard to keep track right now these days. And
Like you within the sensor effective construct all different possible operators and then
right, yeah. So yeah, let me mention also one thing. In the plots where dark matter coupled to the nucleus that I showed, all of them I think were assumed spin independent coupling. So it's like the scalar coupling with the nucleus. But there are also analogous. Typically, the experiments also publish analogous plots for spin dependent coupling. So that might come from different types of coupling in the DVTs. So it has some spin. It couples with the spin of the nucleus. So you might have in your model, dark matter might not have some normal scalar spin independent coupling with dark matter with normal matter, but may have some spin dependent coupling. So in that case, those plots would be, or those exclusion regions would be relevant. So yeah, so there there is still some model dependence. You can have low energy, you can have non-realistic field theory.
So all we have is one number, right, which is very sensitive. There's still all limits. So you can write down an effective theory, but you can only constrain of it. All we can match to,
Yeah.
In that sense, we don't have too many methods. Right? You can put limits on all. So from the computation perspective, you need to check very basic.
Yeah.
That is it. And you were implying different materials to do that. Right. So I was very curious in so in the gravitational limitation also people try to do that. So they want to leave it very basic and they use the smart methodology thing like squeezing and things.
Yeah.
So something like that.
Yeah.
So cannot we use the same thing to detect a solution? So primary goal is to detect these things.
Right.
So
yeah.
So cannot we do this same kind of thing
Yeah,
here?
Yeah, that's a very good point. So today I did not talk about wave-like dark matter. So in the first plot, if you remember, I showed to the left there was a red region, which was I was calling wave-like dark matter. So this was all about particle dark matter. But in the wave-like dark matter, the experimental strategies are very different. You're trying to typically you could use radio cavities or LC circuits for this kind of to detect this type of dark matter. So one idea is to use actually the gravitational wave interferometers like LIGO to detect axion. So the theory of axion is that axion couples to the photons, but the coupling is not like the normal coupling, which is the coupling is like axion FF tilde. So it's a parity violating type operator. So it couples to the two different polarizations, right circular polarization and left circular polarization. So the axion coupling to these two different polarizations are different. So you can use that, and you will have some signature, observable signature, if axion is dark matter in gravitational wave interferometer. So there is one idea like that, and there are corresponding limits from that in the axion parameter space. So yeah, so we can actually use, and people have already used that.
I'm saying this because quantum mechanics puts this to the biggest possible signal. So since you were searching for the materials, we better to go for the with the best strategy what we already done on the quantum.
Yeah, are you talking about the quantum noise limit?
Yeah, exactly. So we can already.
Yeah, that's already been discussed in some of these devices, which are actually, but most of them are in the axion detection part. Axion experiments, not so much in the particle dark matter, but yeah.
So going back to your where you considered the constraints for the spin independent dark matter cross sections.
Okay.
The direct detection, So there, did you like, for the theory predictions, are you considering any like higher order electroweak corrections or something like that to the dark matter? Like for example, I know that for slightly higher masses, I'm not so well versed about like GeV or lower mass dark matter, but for higher mass dark matter, I know that the electroweak corrections would be quite large for a lot of different masses of dark matter. So such things like
As-
taken into account.
Yeah, so you are talking about those model curves in the dark matter
So
nucleus.
that these, the ones that you derive are agnostic about those things, right?
Right, yeah, the experimental limits are, they have that just the cross section as a free parameter, so they don't care about that. But the theory curves, I'm not 100% sure, but I'd be very surprised if they took into account the electric corrections.
Yeah.
Usually people do not.
Usually that,
Yeah.
but they are, for many models, I was even quite.
It could be quite nice sometimes. Yeah, I totally agree with that.
Because of any hidden parameters which do not come about at leading order, they can like.
Yeah.
Like,
Yeah, exactly.
quite large.
Right, right.
Uncertainties.
Right, yeah, some process might not happen at tree level, but in loop level, there could be some extra contribution. So, yeah, but even today, I don't think many groups consider loop level contributions in dark matter.
Questions?
Thank you very much.
We'll be tomorrow, evening, I guess, and 104. We can stop the Zoom.
Yeah,
Are there any other people?
I don't think so.
Hi, I'm Steve. Nice to meet you. Sorry, I missed some part of your talk, so are we going to chat now or you have the time now? If you have other things, we can do it later, but.
No, I'm free. I can talk to you.
Have your tea,
Oh,
or is it gone cold?
I don't know. Yeah, it's
We
pretty
can
cool.
heat it up, there is a microwave downstairs, or you want to go grab some tea there on the other side?
It's hard for me to carry all this right
We
now.
can put it in my office and then.
Okay, let's just take this.
This you can leave it. We can go get some hot tea there.
Okay, sure.
What
I'll
we try,
just take
the
one
biscuit,
tea.
you know, take more. Because they may have some snacks, but I'm not sure. Yeah, I think they should have some. Or if you'd rather just talk, we can stay here and talk and then we heat up this tea downstairs, whatever you prefer.
Well, I can go and.
Okay, yeah, then maybe we, some, find relaxed.
Yeah.